Welcome to Classes with Atish. Today we will solve some problems in dynamics using Newton's first law, second law and third laws, and the concepts that we learned about how to go about drawing a free body diagram. So hopefully you have revised those lectures from dynamics. If not, I will put the link up here so you can take a quick look before attempting to solve these problems. What I will encourage is, after the question is displayed, maybe you can take a pause and attempt to solve it on your own and then see if you got the right answer. Okay, so I'll put the first question on the board. So it says a bullet of mass 20 gram has an initial speed of 1 meter per second. Okay, just before it starts penetrating a mud wall of thickness 20 centimeter. If the wall offers a mean resistance of 2.5 into 10 to the minus 2 Newton, the speed of the bullet after emerging from the other side of the wall is close to. Okay, so let's see. So here's a bullet that penetrates a wall which is 20 centimeter in width. Okay, and the wall offers a mean resistance. So let's write down that force, 2.5 into 10 to the power minus 2 Newton. Okay, the mass of the bullet, that says M, is 20 grams. And that initial velocity U is 1 meter per second. We have to find out what would be the velocity of the bullet V when it emerges from the other side of the wall. If the resistive force is 2.5 into 10 to the power minus 2 Newton, we can write force equals mass times acceleration. So if I divide force by the mass of the bullet, then we will know what is the negative acceleration that is acting on the bullet, right? So the force is 2.5 into 10 to the power minus 2 Newton. Mass is 20 grams, so I will have to convert into kilograms, 10 to the power minus 3. So that many meter per second square. Okay, so this becomes 25 by 20. 5 by 4 meter per second square. This now reduces into a kinematics problem. We can use the formula V square equals U square plus 2AS. Now in this case, V is unknown, so V square, U square is known, okay, and acceleration is minus, so minus 2AS. So we have to find V, so and everything else we have. So U is 1 square minus 2 times 5 by 4, and the distance to travel is 20 centimeters, so 10 to the power minus 2 meters. Okay, so this becomes 1 minus 2, 10, 50, 0.5 or 0.5. So V is 0.707 meter per second. The correct answer then would be option D. Okay, next question. So it says the pulley arrangements of figure A and B are identical. The mass of the rope is negligible. In figure A, the mass M is lifted up by attaching mass 2M to the other end of the rope. In figure B, M is lifted by pulling the other end of the rope with a constant downward force F equals 2mg. The acceleration of M is the same in both cases. Is it true or false? Okay, so in the first case, for case A, if I draw a free body diagram of mass M, mg is acting here, tension is acting here, And if I draw a free body diagram of mass 2 mg, force is acting here, tension is acting here, and the acceleration is this way. So obviously this is accelerating like this. Okay, so we know T minus mg is equal to ma, and 2 mg minus T is equals to 2 ma. Okay, if I add these, so mg equals 3 ma, or a equals g by 3. Okay, so this is case 1. Now let's look at case B. The free body diagram of mg remains same. Okay, there is some tension there, and let's say this acceleration is a dashed. Okay, now the free body diagram of, okay, now here's the catch. There is no mass here, it's only a force that is acting, right? So that force is F, and there is a tension T. Okay, and this is accelerating, let's say, with a dash. So basically the string is moving down by a dash, there is no mass there. So here now T minus mg is equals to ma. I should just remove this, because this free body diagram that we drew is of the string, of the end point of the string. Okay, so let me clarify that. This is end point of string. Okay, there is no mass there, and the string is massless. Okay, so all we can infer from here is F equals T. There is no acceleration happening, because if there is no particle there, there is no acceleration. So all we can say is F equals T. Okay, so now F, now they have mentioned, is 2 mg. Okay, it can be anything, but here in this example they have mentioned 2 mg. So if we add up these two equations, so basically we replace T with 2 mg. So 2 mg minus mg equals ma, or mg equals ma, or a equals g. Okay, or in fact this should be a dashed equals g. Okay, so that is the difference. So the answer is false. Both the accelerations of case A and case B are not the same. Let's look at the next question. So two blocks of mass 2.9 kg and 1.9 kg are suspended from a rigid support S by two inextensible wires, each of length 1 meter. The upper wire has negligible mass, so we can ignore the mass of the upper wire, but the lower wire has a uniform mass of 0.2 kg per meter. The whole system of blocks, wires and support have an upward acceleration of 0.2 meter per second square. The acceleration due to gravity is 9.8 meter per second square. Find the tension at the midpoint of the lower wire. Find the tension at the midpoint of the upper wire. Okay. Alright, so let's draw the free body diagram of, so actually let's cut the lower wire at the center. Okay, so you have half of the wire and then 1.9 kg, so which is, let's say 1.9 kg, and half of the wire would weigh, this will weigh 0.2 kg per meter. So for half a meter it will be 0.1 kg. Okay, And because it's a uniform wire, we can assume that the center of mass is somewhere here, but it doesn't really matter. Now, at this point, there is a tension, right? So if I draw the free body diagram of this point, then there is a tension in the string, let's call that T1, and then there are two weights downward. One is 1.9 G, another is 0.1 G. Okay, and that entire system is moving up with an acceleration 0.2 meter per second square. Okay, now let's look at the upper string. So upper string also has another T tension T dash, and there are two weights that are pulling it down. One is the weight of the entire string. So if the string is 1 meter, so that is 0.2 G. Then there is another third weight actually. Then we have this 1.9 G, and we also have the 2.9 G. Because we should have drawn the diagram first. So this is the upper string, then we have the 2.9 kg here, then we have the lower string which weighs 0.2 kg, and then we have the lower mass which weighs 0.9 kg. So all of these weights, the string's weight and this weight is supported by T dashed, and this is a massless string, so everywhere the tension is same. However, this string, this lower string, because it has mass, everywhere in the string the tension is not the same. Okay, so that's the distinction. This entire system is going up with acceleration 0.2 meter per second square. Okay. Okay, so now let's write the equation for this system. So T minus 1.9 G minus 0.1 G is responsible for the acceleration of the entire system, which is 1.9 plus 0.1, so 2A. Okay, so tension then is 2A plus 2G, so 0.4 plus 19.6 is 20 newtons. Okay. Now let's write the equation for this one. So T dashed minus 2.9 G minus 1.9 G minus 0.2 G is responsible for all the masses moving up with acceleration A. So that would be, so 5 is the total mass in kg, and then the acceleration A. Okay, so T dashed is then 5A plus, how much is it, 5G, or 5A is 1 Newton and 5G is 5 times 9.8, that is 49 Newton. So the answer is 50 newtons. Okay. Okay, let's look at the next question. A block of mass 5 kg is pushed in case A and pulled in case B by a force F equals 20 Newton, making an angle of 30 degrees with the horizontal as shown in the figures. The coefficient of friction between the block, the floor is mu 0.2, the difference between the accelerations of the block in case B and case A will be. Okay. So case A is there is a block and it is being pulled with force 20 Newton, making 30 degree. Okay. And case B is there is a block. It is being pulled like this. Force is 20 Newton, and this is 30 degree. So we have to find the difference in acceleration of block in case B minus case A. Okay. So let's draw the free body diagram of this block first. Okay. So this block has mass mg. Did they give the mass of the block? So mass is in both cases is 5 kg. Okay, so mg. Then there is a normal reaction from the surface on the block. So remember, we have to draw or identify all the forces that are acting on the block. Okay. Now this force is 20 Newton, 30 degree from the horizontal. So it will have two components. One component is like this, which is F cos 30 degree, and then there is another component which is downward, which is F sin 30 degree. Okay. And then finally there is a frictional force also. So because the block is moving that side, the frictional force will be on the other side. So that will be mu times N. Okay. Now let's draw the free body diagram of this case. We have mg. We have a different normal reaction here, N dashed. We have F cos 30 degree in this direction, and then we have F sin 30 degree in the upward direction, and then the body is moving this side, so the frictional force, which is mu N dashed, is in the opposite direction. Okay. Okay, so now let's write the equations of Newton's laws, right? Because there is no movement in the y direction or the perpendicular direction, then N is equal to F sin 30 plus mg. Okay, and okay, there is acceleration in this direction here and acceleration in this direction here. Okay, now F cos 30 degree minus mu N is responsible for the acceleration of the body, so ma. Similarly here, if there is no movement in the vertical direction, so F sin 30 degree plus N dashed must be equal to mg, and here F cos 30 degree minus mu N dashed is responsible for the acceleration ma dashed. Okay, now we have all the values, we can solve and figure out, we have to find out a dashed minus a. So let's put down the values now. So in this one, N is equal to how much? F sin 30. F is 20 Newton, sin 30 is 0.5, plus mass is 5 kg and G is 10. So many newtons. Okay, so 10 plus 50 is 60 newtons. Okay, now So F cos 30, F is 20 Newton, cos 30 is root 3 by 2 minus mu n. Now the coefficient of friction mu is 0.2. So 0.2 into n is 60 Newton. Okay, so we got this equals m is 5 times a. 20 times 0.5 is sin 30 plus n dash is 5 times 10. So n dashed is 50 minus 10 is 40 Newton. Okay, F cos 30. So F is 20, cos 30 is root 3 by 2 minus 0.2 into 40 is 5 times A. So this is again 17.3 minus 8. I made a mistake here. So this should be 17.3 minus 12 is 5A. So A is 5.3 divided by 5. So 1.06 meter per second square. Coming back here, this is equals to 5A or A equals 9.3 divided by 5 is 46 meter per second square. In fact, I should have done A dashed here. So we have to find A dashed minus A, so which is 1.86 minus 1.06 is 0.8 meter per second square. So the answer is option C. So here's the next question up on the board. A uniform rope of length L and mass M lying on a smooth table is pulled by a constant force F. What is the tension in the rope at a distance L from the end where the force is applied? So we have a rope which is length L. Okay, it weighs M, so mass is M, and it is on a smooth table, so there is no friction involved, and this rope is being pulled by a constant force F. Okay, so question is, at a distance L, small l, from this end, what is the tension in the rope right here? Okay, so to find out the tension at this point, let's first figure out what is the acceleration of the entire rope, right? So because the force applied is F and the total mass of the rope is M times the acceleration will give the force. So the acceleration of the rope is F by M. Okay. Now each point on this rope is accelerating with the same acceleration because it's a continuous rope. So at this point, if we want to find the tension is responsible for acceleration of this part of the rope. Okay. Because if we cut it here, then there is some tension here, right, of this part of the rope, and that is responsible for this acceleration. So can we write T equals whatever the mass of this part is times A? Now what is the mass of this remaining part? It is M by L times L minus L, big L minus small l, times A. So now if we equate the accelerations, so F by M becomes T by M by small l, big L, times L minus small l. Okay, or we can write T equals times F, or we can further reduce this into 1 minus L by L times F. Okay, let's look at the next question. I will have it up on the board. So it says a string of negligible mass going over a clamped pulley of mass m supports a block of mass big M as shown in the figure. The force on the pulley by the clamp is given by. Okay, so here for a change we have this pulley which has some mass. Okay, this rope or string does not have any mass. Okay, this is a good problem. So if I draw the free body diagram of this big M, it is pretty simple. There is the pull due to gravity and there is tension in the string, and this tension is equals to mg. Okay, now if I draw the free body diagram of this pulley, so it is being pulled by the same tension downward direction. It is also being pulled by the tension here, which is same because it is a continuous rope and it's a massless rope. Okay. In addition to that, this pulley itself has its mass. So there is another downward force which is small mg. Okay. And because of this clamp, then the clamp, let's assume, is exerting a force on the pulley in this direction, because these forces need to balance. The pulley is not going anywhere. So it therefore means that all these forces are balanced. The only way it can balance if there is a force from the clamp in this direction. Okay. So all of these are balanced. So it means this tension is capital Mg, this tension is capital Mg. Okay. So the vector summation of this and all the forces in the downward direction must equate F in the opposite direction. So we can write F squared is T squared plus T plus small mg squared. Making sense? Yeah. So T is m square g square plus, I can write m plus m square g square. Okay. Or we can write the force is G, we can bring it outside, square root of m square plus m plus m squared. So that is the answer. If you have noticed, I have kept these few rules right here. I have not erased this because now the problems that we are going to solve, we will need to use this algorithm. I like to call this an algorithm. I want to keep this right here for reference, so you can refer to this anytime you are solving the problems. Okay. Next question is really a good one. Okay. So I'll put it up on the board. So two blocks A and B of masses MA and MB are kept on the table as shown in the figure. The coefficient of friction between A and B is 0.2 and between B and the surface of the table is also 0.2. The maximum force F that can be applied on B horizontally so that the block A does not slide over the block B is what we have to find out. Okay. So first step is decide the system. Let's decide that our system is A plus B. Okay, both together. So let's identify all the forces acting on A and B together, external forces acting on A and B. So obviously we have this force. Okay, there is mass of A plus mass of B times G. There is a normal reaction N from the surface of the table, and because both A and B are moving to the right, there is a frictional force to the left. Okay, and one thing to note, this is not in equilibrium. This entire system is moving to the right with an acceleration A. Okay, now let's write the equations. So obviously a normal reaction is equals to MA plus MB into G. This force F minus this frictional force small f is responsible for the entire system moving to the right with acceleration A. So we can write MA plus MB times A. Okay. Now, so from here we can write, we have been given the forces. The friction is mu n. Okay. So we can write F minus mu times MA plus MB G equals MA plus MBA. Okay, now let's substitute the values. Mu is 0.2, MA is 1, MB is 3, G is 10, MA is 1, MB is 3, and A. So F minus 4 times 2 is 8 equals 4A, or we can say A equals F minus 8 by 4. Okay? Okay. Now let's consider the system as A. Okay. Now let's look at this a little bit better. B is accelerating, so is A accelerating. Let's say A is now slipping on B. Okay. Now, if A is slipping on B with respect to B, A's velocity is towards the left side. So obviously the frictional force that will act on A is on the right side. Okay, but here is a catch. If B is accelerating and if my frame of reference is B, listen to this carefully. B is accelerating and my frame of reference is B, then B cannot be an inertial frame of reference. So to make that an inertial frame of reference, we have to introduce a pseudo force opposite to the direction of F. So when we draw a free body diagram of A in the frame of reference of B, we have to introduce this pseudo force F dashed opposite to F. So this is a pseudo force. Okay. Now this is MAG. There is some normal reaction, let's say N dashed, and kinetic friction. So if A is sitting on another block B. Both are moving forward, but this is moving forward in a faster way than this. Then compared to B, so with respect to B, if I make B stationary, this guy will feel like it is moving to the left. So remember one thing about kinetic friction is the direction of kinetic friction is always opposite to the direction of relative motion. So because the relative motion is that side, the frictional force is to the right. Okay, so this frictional force should be to the right. Okay. Okay. Now how can we find this pseudo force F dashed? Well, F dashed is a force on the body A, and A is accelerating with acceleration A. So that is F dashed. Okay. And what is this kinetic friction Fr? It is nothing but mu n dashed or mu m a g. Now for slipping to happen, F dashed must be greater than equals to Fr. Only then the body is moving to the other side. So in the limiting case, we can write F dashed equals to Fr. So F dashed is ma times a, and Fr is mu ma times g. We can cancel out ma. A, now we have F minus 8 divided by 4, and this is 0.2 times 10 or 2. So F minus 8 becomes 4 2s are 8, or F is 16 Newton. Okay, so that is the answer. Okay, let's look at this next question. So I'll put it up on the board. Two identical ladders are arranged as shown in the figure. Mass of each ladder is m and length L. The system is in equilibrium. Find direction and magnitude of frictional force acting at A or B. Okay. We have the ground. We have one ladder like this, another ladder like this. There is a mass hanging from the midpoint. This is M, point A, point B, point P. The length of both these ladders is L, and this is theta. Okay. Let's take this ladder AP first. Okay, so here's AP, the ground. Now this point P on AP supports half of this mass. Can we say that? M by 2G, because the other half is supported by PB. Okay. The mass of the ladder acts downward from the midpoint of the ladder, so mg. Okay, m is the mass of the ladders. Okay, now, so there is a normal reaction, let's say N1 here, and the ladder will try to slide like this. So if this point's motion is this side, frictional force will be which side? This side. So So let's say this is the frictional force. Are we missing any forces? So decide the system. We decided the ladder is my system. All parts of the system must have the same acceleration in magnitude and direction, which is right. It is anyways in rest, so it doesn't matter. Identify all the forces that are acting on the system. We identified several forces that are acting on the system. I think two more forces we should identify is, because this guy is leaning on the other ladder and vice versa, there must be two components of, we don't know the direction of the normal reaction. So let's say there are two components. One is N2, another is N3. Okay, cool. Now similarly, let's draw the free body diagram for the other ladder. It will pretty much be identical, but let's draw it anyways. So this is point P, this is point B. The point P is supporting half of this weight. The ladder itself has its weight mg. There is a normal reaction. This should be same as N1. No reason why it would be different. Now this one is trying to slide outside, so the frictional force will be this side. This frictional force also will probably be the same. Now, if ladder PB exerts N3 on AP, then this will be opposite in direction N3. Similarly, N2 will be downward direction. That's the only difference. Okay. Now, if we got the free body diagram, we have identified all the forces, we can write the equations based on Newton's laws. Okay, now everything is in equilibrium, there is no acceleration anywhere. Okay, so all the vertical forces and the horizontal forces for each of these systems should cancel out. So what are the vertical forces here? N1 in the upper direction, N2 in the upper direction, okay, must be equals to mg, which is in the downward direction, and m by 2g, which is also in the downward direction. Okay, now all the horizontal forces must also cancel out. So this friction must be equal to N3. Okay, now let's write another set of equations here. So vertical in the upward direction is only N1. In the downward direction is N2 plus m by 2g plus mg. Okay, and friction is N3. Okay, now there is another equation that we can write, and that is based on the torque around any point. Okay, now because there are several forces acting on a extended piece of mass, there will be moment, right? So if I take a moment at point P, there is this mg trying to pull it like this, N1 trying to pull it like this, the Fr friction trying to pull it like this, right? But we know the system is in equilibrium, so tau P must be equals to 0. So if we are calculating tau P, all these forces don't count to the moment, but mg does. So mg times, what is the vertical distance from P? Like this distance. This is L by 2. This is theta. Okay, so L by 2 cos theta. Okay, so that's the moment because of mg, and it is trying to pull it in this direction. Now Fr is also trying to pull it in that direction, So plus Fr times, what is the vertical distance? Is this, which is L. So this distance is L sine theta. And that must be equal to N1, which is trying to pull it in the other direction. So must be equal to N1 times, what's the distance between N1 and P, is this, which is L cos theta. Okay, now our job is to find Fr. Okay, let this equation be 1 and this equation be 2. And this equation is 3, let's say. If I do 1 plus 2, 1 plus 2. So 2 and 1, n2 and 2 gets cancelled out. Okay, it becomes 2 mg plus mg, half mg and half mg. So n1 we found is mg plus mg by 2. Okay, now let's substitute this here. Okay, so then in fact we can cancel out L, L, L. Let's divide both sides by cos theta. So that becomes mg by 2 plus Fr tan theta equals n1, and n1 is mg plus small mg by 2. So Fr tan theta is, so if I bring this one here, so this becomes mg by 2. So basically we can write m plus m by 2g. Okay, so Fr then becomes m plus m by 2g cot theta. Oh, we should have actually written in proper notation m plus m by 2 cot theta times g. Okay, so that is our answer. Okay, so this one will be the last problem in this series that we'll solve for now. Overall, all the problems that were solved will help you clear out a lot of your concepts. So make sure you revise them and try them on your own. This is the last question that I will put up on the board. So two masses M1 and M2 connected by an inextensible string over a frictionless pulley are moving as shown in the figure. Okay. The coefficient of friction of horizontal surface is 0.15. The minimum weight M that should be put on top of M2 to stop the motion is. So here's a pulley, massless pulley. There is one mass here, massless string, another mass here. This is M1, this is M2, and this guy is in motion for now, so there is some acceleration that is happening. Now, what is the mass M that should be put on top of this to stop this acceleration? That is the question. Okay, so first let's take M1 as my system. So system M1. Okay, this is fairly simple. There is gravity working and there is tension in the string. Okay, and supposedly we have already put this mass M on top of it, so it is in equilibrium right now. So tension equals m1g. There is no acceleration. Okay. Now let's take our system as m plus m2. Okay. So obviously the weight is m plus m2g. There is a normal reaction n. Now if it was moving this side, okay, let's write the tension first. So it's same tension T, because this tension and this tension is same, because it's a continuous string and it's a massless string. Okay, and even the pulley is massless. Now since the motion before it stopped was in this side, the frictional force is on the other side. Okay. Now when we put the mass m just before it stops moving, up until then the frictional force is there. So in the limiting case we'll still consider the friction there. Okay. Now this, so if we write the equations now, n equals m plus m2g. Okay, and T minus Fr should be equals to 0, or T is equals to Fr. Now what is Fr? Fr is mu times n. Okay, so from here we can write T equals Fr. We have to find the mass m, right? Okay. So and T is m1g. What is Fr? Mu times n. What is n? M plus m2g. Okay, so gg we can cancel out. So m1 equals mu m plus mu m2, or mu m equals m1 minus mu m2, or m equals m1 minus mu m2 divided by mu. So this is 5.15 times 5 times 10 divided by 0.15. 5 minus 1.5 divided by 0.15. 3.5 divided by 0.15, with roughly 23.33 kgs. Okay, this was actually a pretty simple one. The idea here is more problems you solve, more your concepts become clearer and clearer. So my word of advice and encouragement here is solve as many problems as you can, take up from different books, okay, and if you cannot solve a problem, reach out to me in the comments and I will make a video to solve and to show the steps how to solve any problem that you get caught up with. Okay, with that, cheers and good luck.